Yet again, we continue with our network layer module, and today I'm going to be talking about Internet Protocol version 6 or IPv6. So what is IPv6, and specifically what are the reasons why we have IPv6? So actually there are several reasons, and one of them is primary. Obviously we have a problem with the IPv4 address space, and we basically already ran out, as you heard before. But in addition to that, there's also several other reasons. So first of all, there's point to clean up the IPv6 header or IPv4 header to make it a little bit leaner. And the second one is basically introduce some of the new features. So for example, some form of automatic gateway discovery. Managing of IP addresses is also a little bit of problematic, and in IPv6 there is mechanisms to do it. Stateless address allocation mechanism, or SLAAC. And second of all, there's also concept of having multiple IP addresses assigned to a specific interface, and not just multiple IP addresses, but rather these IP addresses basically change over time. Now getting to the actual comparison of IPv4 and IPv6 headers. So I put the headers side by side, and just to highlight. The biggest change obviously is the difference in the address space of source and destination IP addresses. Instead of 32 bits, now we have 128 bits. So like really huge addresses. But as you notice, this size of the header, because of this change, didn't actually change too much. And the reason it didn't change too much because a lot of elements got removed, and not a lot, but at least some portion of the elements got removed. And specifically, IPv6 header is now a fixed header, so there are no longer options anywhere. There are no fragmentation fields, as you can notice. There is no identification, there are no flags, there is no fragment offset, and there are no header checksums. So for the last one, I can just tell you there is no reason for the checksum, because all those checksums actually exist on a higher level protocols. There's something in TCP, something in UDP, as you will experience in Project 3. So there's no really need to have IP checksum. The other two we'll discuss in a few seconds. So, as I said, there are no IPv6 options that you can see on this header, so they're basically not there. But is it really true? Like, does it really mean the IPv6 cannot have any options? And the answer is obviously not really. So it's just the reason how they changed this model. So instead of having options inside the header, now you can have optional headers, so like header extensions. Logically, it's about the same thing. It's just a slightly different mechanism how things been realized. So instead of it's being part of the actual header that's considerably flexible, now it's you can chain headers. And there are several options for these headers. So for example, we still have a special header for fragmentation. So instead of being part of the fixed header, now this is the part of a flexible extension. There is something for routing, something for authentication, and something for hop-by-hop options as well. It is really up to specific specification of individual headers, but majority of the headers defined to be processed by the end hops. Some require at each hop, but with one interesting practical implication. There's very few routers, like big routers, that actually support extensive IPv6 options. So the best bet, if you want your packet to be delivered, your best bet is basically to not include any options, like to avoid fragmentation, avoid any next like hop-by-hop headers, avoid any authentication headers, and so forth and so on. Okay, so that's the idea about the kind of extension of IPv6, but now a little bit of details of how exactly it happens. So the idea behind the IPv6 extension headers is simply some form of a daisy chain. So basically we have this basic header that can point using this next header field that the next header is something else. Like in the simplest case, for example, like if you just exactly have a TCP header behind, then it will be TCP header. If you want to include something optional, so for example, this routing header, then as part of the next header field in IPv6 IPv6 header, you include that the next header is this extension. So basically there is something extension. And in all extensions, there's exactly the same next header field that can be that can point to next TCP header. So basically following extension. And you can actually have multiple of those daisy chaining. So basically you have IPv6 to the routing, routing to ESP, ESP to some potential fragmentation, fragmentation to finally to a TCP header. So this is basically the model of these extensions. And for IPv6 fragmentation, so this one I gave you example, not example, I just got from the IPv6 specification picture of IPv6 fragmentation header, like a fragmentation extension header. And you can see a few similarities to what you already saw in IPv4 fragmentations, but there are a few differences. So for example, one major difference is we have to include this next header field because it didn't exist in IPv4, because in IPv4 that was part of IPv4 header. We still have this M flag, like it used to be called MF flag, but it doesn't matter. No other flags in existence. So there's still 2 bits reserved. It's kind of same 3 bits as in IPv4, but it is 2 bits simply reserved, and there's no option to request no fragment basically. And instead of 16-bit identifier, we now have 32-bit identifier for all different fragments. So this is basically to counter that there are too many, now there can be too many packets in flight, and you want to have a better way to identify individual fragments if you really do some form of fragmentation. The major difference between IPv4 header is not in IPv6 fragmentation is not the header itself, but rather the logic behind the fragmentation. So if you remember, in IPv4, every single system that encounter a packet that it cannot forward further, it will split it. I mean, the packet can be split multiple times at different hops. Not the same for IPv6. So in IPv6 specification, they explicitly define that the packet can only be split by the source and can be only reassembled by the destination. So, which means if some packet at some hop cannot forward this packet, so instead of breaking down further in smaller fragments, it will kind of report some form of an error. To move to a slightly different topic about the address notation. We have 128 bits to represent IP address. This is kind of 4 times more than IPv4 address. So people try to invent a slightly different notation to simplify writing address. So instead of just using how many 16 like, yeah, 16 digits separated by dots, they decided to simplify things. So there, and what we have today is actually multiple different notations of IPv6 addresses, which is slightly uniform compared to what can be done in IPv4, and I hope you remember that lecture. But still, there's a number of ways how you can represent the same IPv6 address. So for example, in canonical way, you simply represent every word, or like every 2 bytes of IPv6 address as a hexadecimal digit, and then separate them with colons. So this is what you see as a first way of representing the address. What can be simplified a little bit, just logically simplified, you can just omit all those leading zeros, and this way you can quite compress the amount of data that you're encoding if your IPv6 address is quite have too many zeros, like too many leading zeros. So that's one way of optimization. There is another way to optimize, which is quite interesting, is to suppress sequential zeros. Because look, we have 128 bits, hopefully not all addresses will be assigned at the same time. So look, if 4, 6, 8 bytes been allocated to some subnetwork, and like a few bits at the end have been allocated for the host, then a lot of things in the middle would be basically zeros. So what you can do is you can simply suppress a sequence of zeros with double colon. And note that you can only suppress one sequence of zeros. So for example, if you have some address that has 000, some numbers, then 000, you basically have to pick and choose which sequence of zeros you will be suppressing. But you cannot suppress both because it will create ambiguity kind of what exactly IP address you're representing. Seemed to be that's it, but then they actually invented yet another way to represent IP address for one specific use case, because people got used to IPv4 addresses. So you can technically represent part of the IP address in IPv6 format and part of the IP address in IPv4 format. And this is the example I'm giving you here, where the last 4 bytes of the IPv6 address is simply represented as normal IPv4 address. And there's a use case for this one if you do some form of IPv4 in IPv6 tunneling. Similar to IPv4, there are several special addresses. First of all, loopback address. As a loopback address, we no longer have the whole /8 allocated, like as in IPv4, and the only address that's been reserved is ::1. And just for the fun of it, I will ask what exactly the canonical representation of the loopback address. Then there are several ranges reserved. There's a range reserved for so-called IPv4 mapped IP addresses, and this one is primarily used internally in a system. So to make sure that your application can support both IPv4 and IPv6, the system on local system usually do a bit of tricks and kind of accept both packets, but your application only receives, say, IPv6 address. And then it's basically trying to map incoming IPv4 address into some semi-fake IPv6 address and kind of give it to you. There are ranges dedicated to various types of tunneling, and this is actually 624 is one of the tunnel mechanisms, and I'll show you a picture with many more. There is a /8 dedicated for multicast addresses. So this is similar to 224 /also 8 for multicast addresses in IPv4. And there is similar to IPv4, there is a link local unicast addresses. So these ones, kind of in principle, they're similar, but they're used way more extensively in IPv6 than in anywhere in IPv4. Major difference now. If you remember, in IPv4 we have 2 special addresses, like a kind of beginning of the range, end of the range, with a special meaning. One representing the network, the other representing the broadcast. They do not exist in IPv6. So, and basically, if you have a /129, you can have 2 valid IP addresses, and you can use both of them to assign to a specific host. If you need the function that similar to broadcast, you have to use some form of a multicast. So that's basically the idea of improvement of the protocol. So they simply remove the concept of broadcast, but replaced with the multicast capability. And there are small differences in very small environments. It actually doesn't matter. Like your multicast packet will reach everybody, but there are environments where multicast actually performs better, because you can subscribe to multicast group, you can unsubscribe from the multicast group, or like you can pick and choose which multicast group you're actually interested in participating in. And there are a few exercises just in the lecture, just for you to practice a little bit more with IPv6 addresses. IPv6 has a reasonably small kind of deployment, this is around 25%. So we still want to use IPv6 in some form. We still want to transition to IPv6, but we need some form of a path. And what the researchers, what the engineering community come up with is actually huge number of solutions, and maybe not huge, but a reasonably large number of solutions that trying to get to that goal. And the first step that was introduced is the so-called dual stack. So basically, one host can support both IPv4, IPv6, and kind of depending on which application you run, you will have like either IPv6 application, IPv4 application, or some kernel already highlighted with IPv6 mapped IPv4 addresses. It actually can simplify this process by kind of having a dual stack on the system, but for applications always presenting itself as IPv6. So that's kind of one of the basic models. But from the other perspective, you still want to have ability to connect to IPv4 network if you only connected to IPv6, and vice versa. If you only have a connectivity to IPv4 network, in principle, you want to get access to IPv6 network. So this way, we want to get connected, basically. And so they try to cheat in different ways, because like normally network layer is the one that connects everything, is the one that have to be common in all places. So they had to cheat in the form of the tunnel. So basically there are some portions of the network support IPv4, some portions of the network support IPv6, and you create some form of a tunnels between them. Like if I try to draw some kind of a picture, so let's say this would be IP4, this would be IP4, and then some network in between IP6. You can technically create a kind of logical tunnel, some form of a tunnel that goes through IPv6 and goes to another IPv4 network. So you can do this, or technically you can draw the picture in different way, where you have a kind of satellite IPv6 network and only IPv4 network in between, and you have a tunnel of this. And I hope you kind of got some idea behind kind of the tunneling, and this reflects in the naming. So you can do 6 to 4, you can have 6 in 4, you can do 4 in 6. I'm not sure there is a 4 to 6, but there are tons of different interesting names of those protocols and different mechanisms. So those kind of processes. There is several so-called network address translation protocols developed. So this one's, the one that I listed on slides, are actually quite different from NAT that we talked last time. And they do translation, so don't get me wrong. So they have the kind of, you give them IPv4 address, they try to rewrite to IPv6 address, but they, at least NAT64 also involves DNS. So it's kind of, it's kind of trying to go to some website that only has IPv4 address. But your local DNS kind of doing this lookup, figure out, oh, there's only IPv4 address available, but it's, instead of returning you the right answer to the DNS query, it actually gives you a wrong answer, which lists IPv6 address, especially formatted IPv6 address. Because your stub resolver is kind of dummy enough, it simply accepts all the answers that the cache resolver gives you, then kind of your browser will try to go to that IPv6, try to connect to that IPv6 address. And somewhere in the middle, there's a box that actually converts that IPv6 address to a real one. In any case, that's a kind of interesting highlight. If I'm going to ask any questions, I'll just try to ask in general about the tunneling, how things generally work, or what is dual stacking in the first place. Will IPv6 get deployed eventually? Yeah, probably. We're still getting every year, we kind of, the amount of deployment increases. They're still getting pressure from exhaustion of IP addresses, so kind of new ISPs coming in. They have kind of urgency to give their customers internet connectivity, but they cannot do it in IPv4 addresses because they simply either have very limited IP addresses, or they don't even have IPv4 addresses. So then they simply request blocks of IPv6 addresses, get them, and kind of do some form of NAT mechanisms to actually give access to the internet. This basically highlights the complexity versus time. Like as of right now, we have some number of IP addresses still kind of left. It's still hard to manage that, but people somehow coming by, like, of those IP addresses still allocate, everything is still working. As time goes by, this problem becomes more and more complex. It's much more costly to get whatever blocks of IP addresses on some IP address black market, and people will start transitioning more and more to IPv6. So eventually we'll get to the point, but to give you some perspective on IPv6 status, I captured the picture of number of IPv6 blocks currently in use in the routing system, and this one just tells you that around 80,000 IP addresses are actively used today on a global scale, and you can see that even in the last 2 years the number of prefixes has increased by like 20,000, and the overall picture is quite, I wouldn't say it's exponential, but it's doing something very rapid. And however, if I compare IPv6 to IPv4 addresses, like this is IPv6 to IPv4 address subnetworks in a routing table, then this relationship is quite small. So as you can see, in one case it's 800,000 prefixes in a routing table, and in the other case it's kind of merely 80,000. So it's a 10 time difference. However, this picture may not be exactly representative, and for one specific reason. IPv4 prefixes are much smaller. And if some company, if some ISP wants to kind of have a larger space, it basically forced to advertise multiple prefixes. Like even it's from the same place, in the same building, it will have to have presence of multiple prefixes in the routing table. So that's potentially inflates the size of the routing table. And a more realistic picture, and that's where my number of 25% actually coming from, is looking at the ES numbers. So like some number of ISPs that actually have deployment of IPv6. And this number is a little bit better than the prefixes. In case of IPv4, we have a little bit less than 70,000 those ISPs in existence. And for IPv6, we have a little bit less than 20,000. So if you divide it, would be like around 25% coverage. And as you can see, I actually cannot see that the gap is decreasing, but hopefully at some point it will go in decreasing fashion. So and a deployment of IPv6 will go up. This was IPv6. What I want you to remember is kind of basic differences between IPv6 and IPv4. So remember, there's a different address space, there are some cleanups, and they actually reinvented the options using these special headers, and then you can daisy chain them. There are a few interesting special functions that were introduced in IPv6, like for example this automatic gateway discovery, having multiple IPv6 addresses, and technically this capability kind of got backported into IPv4 world. And this SLAAC, and just for the fun I will ask what the heck is this. But again, we're still a long way for the deployment, before the deployment of IPv6 can be completed. And meanwhile, we have multiple different options to connect to IPv6 network from IPv4 or through IPv4, or connect vice versa to IPv4 if you already converted to IPv6 but still want to get access to the website that is not yet converted. Okay, so that's it, and see you next time.